The evolution of flight from the few to the many, and now even in the control of our own hands. As more and more people have access to their own personal drones, the number of malicious and illegal drone attacks are increasing and targeting large crowds. Current solutions pose issues. Using birds of prey for capturing receives outcries from animal activists. Net guns require accurate aim. There are companies that have stadium defense systems, but their website doesn't work, so we couldn't really contact them to ask for a quote. The world needs a defense system to protect people against drones for commercial use. This is the age for drone development. The RAPTOR system provides real-time aerial potential threat observation and resistance. We want a budget-friendly solution that protects civilians. So let's take a predetermined area and divide it into a certain number of sectors. An enemy target drone will fly into one of the sectors. The ground detection units have motion sensor detectors that detect motion, and when it's triggered, it will send about 5 seconds of video feedback to the base station. The base station runs the machine learning model algorithms, and if it decides that a breach has occurred, then it deploys our defense drone to that sector. Our objectives for this ambitious proof of concept involve: develop a custom drone from scratch, have a ground station that can monitor and detect enemy drones. When the RAPTOR system receives event triggering of a breach, the defense drone should autonomously fly to that sector. So how do we approach our design? Drone development! For the RAPTOR system, we developed a custom drone made from scratch based on the sturdy, powerful Crossfire 2 open source project. We also 3D printed parts for the frame. The drone runs on a BeagleBone Blue board. For autopilot capabilities, we implemented ArduPilot open source software. Machine learning drone threat detection. For our target enemy drones, we are using cheap hobby shop quadcopters. When creating our custom dataset, we not only scraped images online, but we also went outdoors to capture some images based on the types of quadcopters we test with. After processing our dataset of over 1,375 images, we trained our model with TensorFlow GPU, and of course we did a lot of testing with our drone detection model. Flight. So we have a drone, but can it fly? Initially, we tested with the drone controller. Some challenges we faced include not being great at piloting drones. After configuring GPS capabilities, we were able to use Q ground control for mission planning. We successfully achieved autonomous flight with our drone system.
How is landing? It's gonna land. It's coming. No, maybe not. I don't know. It says land, but I have no way to tell it to land, to be honest.
Oh gosh!
I think that's landing. I don't know. I hope so. I'm gonna go with that to land. Or the battery's dying, one or the other. It did it!
However,
Good beauty and she's great. Ah!
whoa! Oh no! On the weekend before senior design deadlines, our drone perished. With finals coming up, we had to complete our year-long senior design project in 3 days. But UAH computer engineering students can do anything. Within the hours leading up, Team RAPTOR worked hard to make up for the lost time and resources. Every part had to be reprinted, and relying on a single 3D printer to handle a huge load was cutting it close. A huge thank you to our sponsor, SMAP, for letting us use their 3D printers after our drone's frame shattered. Lessons learned. Failure provides a unique opportunity for education. The RAPTOR system, pioneering the future of drone innovation.